All right, so we're going to talk about constant rates of change. We know what the word constant means. It means that something doesn't change. And now a rate of change, we talked about back when we were doing proportional relationships, back in chapter 4, we talked about having a rate proportion. A rate means something's changing. It means how quickly is it changing, how fast is it changing. A rate can be a speed. A rate can be maybe how quickly someone can make something, which is kind of speed. Like I can make 3 bicycle seats in 2 hours, so my rate is 3 seats in 2 hours. So we're going to talk about when that rate is constant. It's going to be constant just like it was when we did proportional relationships. Except when we talk about linear relationships, like when we talk about a constant rate of change, being as the rate of change of a linear relationship, they're not always going to be directly proportional. Most of the time, when it's something simple, they will be, but sometimes they won't always be. The way you know is if you have an equation, as a side thought real fast, if you had an equation like y equals 2x, that will be, it'll have a constant rate of change and it'll be directly proportional. Just like we talked about in chapter 4, how to tell if something's proportional or not, meaning is the ratio of this to this the same as this to this? And for this one it is. But if you had an equation such as y equals 2x plus 3, because we added that plus 3 part, it would no longer be a directly proportional situation, meaning these ratios wouldn't all be the same. And by the way, I just made these up. These have nothing to do with these over here. I just want to make sure you know the difference between constant rate of change for a linear relationship, because both of these are lines, meaning they're linear. We practiced at the beginning of chapter 5 graphing linear functions with input-output tables. We would find that this one would be a straight line and this one would be a straight line. They would both just start at different places. This one, a quick sketch of that graph for the first one would look like something like that. Just a quick little sketch of the first one. Whereas the second one, as a brief reminder, would start a little bit higher, and so it'd look more like that, where it wouldn't go through the origin like how that one did. It starts further up. So I just want to make sure you know the constant rate of change does not matter whether it's directly proportional or not. I just want to know it's very similar to it. Okay, so when we're talking about rates of change and constant rates of change, what we're going to be doing in this section is identifying what are they, and we want you to interpret them. We want you to first tell me what is the rate of change, and if it's the same, tell me it's constant. Tell me the constant rate of change is, in this example, we would say how many textbooks per student. Now, before I go any further real fast, this table, think of this similar to an input-output table, meaning we normally put x first, we normally put y second, which tells us x is usually the input, y is usually the output. So when you're describing the rate of change, we generally want to hear how many outputs per input. That's what we want to hear. How many outputs? These are the outputs per input. That's what we generally want to hear. That would be a completely simplified rate of change. Very similar to a unit rate. So very often can be a unit rate. So in fact, I'll add that under constant rate of change. Very often, just like a unit rate. Now, the only times it wouldn't be is sometimes when it becomes an ugly answer. Like if it were to be like, let's say a decimal, we don't always do it, but we still can. So just know, it's very often just like finding a unit rate. Just like a unit, I left out the rate part. And that's going to be a constant rate of change. So now let's take a look at this example real fast. In this example, we notice in the table, students is going up by 5, okay, and textbooks are going up by, what looks like 15. Textbooks are going up by 15. So here's what I want you to do. Between any of these, it can be from here to here, or from here to here, or from here to here. I want you to take a look at what is the change in the number of textbooks from each of them. You'll notice each time the change is it goes up 15. So the change in number of textbooks is 15 textbooks. Look at your students for that same gap. Students go up by 5 every single time. So when we talk about rates of change, I said earlier we want to know how much does the output go up or down for every time the input goes up. So in this case, we would say, all right, our textbooks go up by 15, so positive. Our students go up by 5, so positive. So that tells us 15 over 5. That's 15 books Just like when we're talking rates at the beginning of chapter 4, that's 15 books per 5 students. 15 books per 5 students. So that in words, we would say 15 books for every 5 students, or 15 books per 5 students. And that is a rate that we can simplify. 15 over 5, 5 goes into both of them, so that gives us 3 over 1. So we're going to call that 3 textbooks per 1 student, or 3 textbooks for every 1 student, or somehow saying that interpretation. We generally want to know the change in the output per the change in the input. So change in the output per change in the input. And go ahead and simplify it. We like to see them simplified. So that's an example of finding a constant rate of change. Even though technically this was the constant rate of change, it wasn't the fully simplified version where we said 3 textbooks per 1 student, or 3 textbooks for every 1 student. So that's how much textbooks increase by 3 for every 1 student that goes up. All right, let's talk about this example for a moment. In this example, we were given the graph. The graph portion was given. We have our graph. We weren't given the information in a table, or we weren't given the information in a story. But the example says, the graph represents the number of t-shirts sold at a local band concert. All right, local wasn't in there. Use the graph to find the constant rate of change in number per hour, meaning how many shirts were sold per 1 hour. They're clearly telling you they want to know per hour, meaning per 1 hour. Meaning in that last example, when we simplified per 1 student, they will know the same thing here. They want you to simplify per 1 hour, and that's what they're asking us to do. So if you look at the graph, I see a point here, a point here, and a point here. Those are going to be the points of focus for us. Anytime it crosses a graph. And you don't have to choose places where there's a dot already waiting for you. Choose anywhere where it goes through a crossing, by crossing I mean right here. Oh, I missed. Like here, still kind of missed. But that location right there where 2 grid lines intersect, where you can definitely tell the value, choose points like that the line goes through. Okay, so let's see. If we were to just interpret this, we'll talk about how to calculate in a second over here. But let's just talk about it. We know that our x is generally our horizontal axis, or our input, or our independent variable. We talked in a previous video that all those things mean the same thing. X is the input, x is the independent variable, meaning the one you choose. Talk about that in science class as well. And so x is also your domain. I didn't have room for an equal sign. So all those words mean the same thing. Whereas the y or the vertical, that's the y variable is your range, which we talked about, which we don't really need right now, but is your dependent variable, meaning the one that you do not choose. It does not have freedom. It depends on what x is. And it's also your output. So if you know which axis is which, think about what we just said up top at the previous example. We said a rate of change, a constant rate of change is how much the output goes up or down per how much the input goes up. So let's see in this example. Let's use these 2 points for example. The output, which is the up-down, because we saw that's the vertical axis, goes from 25 to 30. So that means the output goes up by 5. Goes up. So the output goes up by 5. So when we made our fraction, that would be 5 over something. Now, if we look at our input, remember our input is our left to right, it's our x-axis, our x variable. It goes from 8 p.m. to 9 p.m., which tells us how many hours went by. From 8 p.m. to 9 p.m., that's 1 hour. So that's going to be 5 t-shirts. I'll put TS for t-shirts, and then in 1 hour. Now, that fraction already is simplified, 5 t-shirts over 1 hour, which means 5 t-shirts per hour. And so you're done at that point. You've simplified it, and that's really all you have to do, so you can count. But I want you to know, even if you did not choose these 2 points, it would still work. So let's take a look at if we chose maybe just those 2 points that are in red. To get from here to here, our output went up by 10. So plus 10 to get from here to here. So our output went up by 10, which means in that same example, we'd have 10 t-shirts over, let's see how many hours. So 8 p.m. to 9 p.m. to 10 p.m. Okay, so 2 hours from 8 p.m. to 10 p.m. So that's 2 hours. So we have 10 t-shirts over 2 hours. Well, that fraction simplifies to 5 over 1, which is 5 t-shirts in 1 hour. So it still simplifies to the exact same answer. So no matter what 2 points you choose on your graph, it will still simplify to the exact same value. Now that's if you're given a graph. If you're given a graph and you can just count, go for it. Just make sure you simplify your final answer, and remember it's output per input. Think of it as the output value, whatever that is. In this case it was t-shirts. How many t-shirts per the input value, which in this case was hours. If you wanted to calculate this, if let's say the graph wasn't available, or let's say the graph was not clear enough, you could use points on the graph. So what this says up here is to find the rate of change, pick any 2 points on the line, such as 8:25 and 10:35, which are the two we just used. Okay, meaning 8 hours and 25 t-shirts, or 8 p.m. 25 t-shirts, or 10 p.m. and 35 t-shirts. Here's what we do. We do the exact same thing. The change in the output, meaning how much did it go up? What was the rate? The change in the output. Well, it went from 25 to 35, which means if you do 35 minus 25, that'll tell you the change is 10, which is also, we counted. That agrees with what we saw visually. Now the change in time. It went from 8 p.m. to 10 p.m. So 10 minus 8, well that's 2, the 2 hours. So that's still 10 t-shirts over 2 hours. It gave us the same thing. This is how you could calculate it. So the change in your output over the change in your input. Simplify, and that tells you your rate of change, which is 5 t-shirts per hour. So this is what we mean by calculating a constant rate of change. Now, I will tell you this. I know these examples, these numbers, you could have maybe done these without the calculations, but remember, we're practicing the process, so do it now so that no matter how hard or easy the question is, you have a method that always works. So take a time to maybe jot down some of these notes if you've not done so already, and make sure that you are prepared and you understand these concepts. So the overall underlying value is the rate of the output how much the output goes up or down, so that kind of rate-ish, per how much the input goes up. The input is always going to go up. We're always going to talk about a left to right relationship, especially when we're talking about graphs. We're always going to do left to right. We're not going to go right to left. So our input is always going to go up from left to right, generally speaking. Let's take a look at some more. Okay, if you think you could do number 1 and number 2, go ahead, pause and take a moment to make sure you can do them. See if you can do numbers 1 and numbers 2. Okay, so let's see. It says find each constant rate of change. Side length. Oop, didn't mean to move that. We're talking about side length, and then we're talking about perimeter. Back to the eraser. Okay, so as side length goes up by 1, perimeter goes up by what? It goes, remember, this would be like our input, meaning how long was it? You chose how long the side was. Or generally the first column is going to be our input. So if you want to even write input right there. And output. Okay, so, and this one goes up by 4. So when side length goes up by 1, this one goes up by 4. So that tells us the perimeter goes up, for every time the perimeter goes up by 4, the length goes up by 1. So our constant rate of change is going to be 4 over 1. So we're going to say perimeter, if they're not giving us units of measure, so just to pretend they're giving us units of measure, let's say those are inches. We could say the perimeter is 4 inches. If we use our words, we could say perimeter goes up. So perimeter increases. We can just use our words. That'll make it more clear. Increases. We'll say 4 inches. Or just 4 if we didn't have a unit of measure. Remember, I made up that unit of measure. 4 inches for every increase of side length. Every 1 unit of increase, we don't know what those units were, but maybe we can say inches. Okay, that would be our constant rate of change. So now try number 2 if you think you can do that one. You haven't tried it yet. Press pause. In number 2, if we use, let's say, these 2 points, the 2 that are furthest away, just to kind of make it a little bit harder, use a different color. So this point and this point, if we use those 2 points, we can say, okay, the output, which would be the miles, goes up from 72 to 80, so 72 to 88. So it goes from 88 to 72. That tells us it goes up by 16. It goes from 10 a.m. to what looks like 2 p.m. So let's see, 10. Okay, take a second to read this graph. Okay, so what you'll see is We've got the 88 minus 72 because it went from 72 miles to 88 miles. So subtract that. Now it'll give us how much it changed vertically, meaning how much did the output go up. Because as a brief reminder, remember, this is your output. Your output generally is your vertical axis or your dependent variable. And then your horizontal axis is generally your input or your dependent variable. I'm sorry, your independent variable is the one you choose, the one down here. All right, anyway, so 88 minus 72, that will tell us that it went up. And so then now let's look horizontal. It goes from, we were talking about one interpret the time. So that looks like 10 a.m., 11 a.m., 12 p.m., 1 p.m., and 2 p.m. And so that make this 3 p.m. Okay, so that means it went from 11 a.m. to 3 p.m., which to doing that with time, that's kind of weird. If it was in military time, it might make more sense. But just kind of reason that through. It went from 3 p.m. from 11 a.m. to 3 p.m., so that's a grand total of 4 hours. So rather than try to write how to subtract the time without being in military time, I'm just going to go ahead and cheat, just write 4. So it had a change of 4 hours. Normally you would actually subtract just like you did up top to actually calculate it. Because with time, rather than try to convert to military time, make your life easy. Just know 4 hours. All right, so anyways, 88 minus 72, well that's 16. So we have 16 miles over 4 hours. Simplify that fraction, 16 over 4 simplifies to 4 over 1. So that means 4 miles in 1 hour, which means our constant rate, our constant, in this case, speed, we're going to say 4 miles per hour, or 4 miles for every hour, which is mph. It's a unit of measure we're used to thinking of. It's a unit rate. Constant rate of change is very often interpreted literally as a unit rate. Let's take a look at another example. All right, we'll make this our last example in finding constant rates of change. So in this example, we're talking about money. In this example, it says Joanne is depositing money into a bank account. After 3 months, there is $150 in the account. So if you wanted to think of that as an ordered pair, that could be 3 months, comma, $150. I'll leave off the money sign. So that's almost like an ordered pair if we were to graph this, as in if months was our horizontal axis, like if we were to do a quick little graph and months was down here, and money was on this axis, we would find 3 months and then we would find $150, wherever that may be. We could actually graph it. Remember, I'm just making up, that's a quick sketch. So in other words, ordered pairs can work. All right, so let's continue. After 6 months, there was $300 in the account. Okay, so as of 6 months, so I'm gonna do 6 comma, there was $300 in the bank account. Oh, I include the dollar sign for that one. You don't have to, but it's not necessarily proper in an ordered pair, but I slipped it in there. And now it's gone. All right, in the account. Now find the constant rate of change of the account, meaning what was the constant rate of change each month in order to get from this value to this value. So we can calculate that. We mentioned that the money is the output or the Y variable, generally speaking, the one that depends on the other. In other words, the money being in the bank account, depositing, she chose how many months to keep putting money in the bank account. The balance she wasn't choosing, it was a result of her putting money in. And she put in money based on how many months she wanted to do it for. So that's gonna be our output, that's gonna be our dependent, or our Y, if you wanna think of it as X comma Y, if you wanna think of it that way. Okay, so when we're working on this example, go away eraser, still there, there we go. All right. So that means if we look at the change, to calculate this change, if you think you can do this one yourself, press pause and see if you can do it. Give yourself a chance. Okay, when working through this one, we look at the change in money. So it went from $150 to $300. So that means if we do 300 minus 150, that will tell us how much it changed. Now some of these numbers may be nice, pretty numbers you can calculate in your head, but just take your time to show your work. Don't be so overconfident that you might make a mistake. Now in terms of months, it went from 6 months, it went from 3 months to 6 months. So subtract that, and that'll tell us how many months went by. So go ahead and do your calculations here. 300 minus 150, well that's 150. And then 6 minus 3, that's 3. So that means $150, I'll even put units of measure, $150 in 3 months. Now that's a rate, $150 per 3 months, or for every 3 months. So we're going to simplify that rate, just like you would a unit rate. We're going to make that have a denominator of 1. We want to know how much money in 1 month, because that's our constant rate of change. So simplify that fraction. 150 over 3, well, 3 goes into both of those. So you're simplifying fraction skills, divide by 3, divided by 3. So $50 goes into 153 times. So that's gonna be $50, and 3 goes into 3 one time, so 1 month. So that means $50 per month. So you could say she deposited, remember, interpret it in the context of the question. She deposited, I'll include she, $50 per month. That would be the constant rate of change, and that's also going to be your unit rate. Like I said, most often they're very similar. So now, take a moment to think about this problem. In these types of scenarios that we've now gone over, where we've talked about constant rates of change, remember, these are only specific when you have a constant rate of change, meaning every single time your input goes up, or X, or whatever you're measuring, every single time that goes up, if Y is going up by the same amount every time, you're going to have a straight line. And we found that when we were talking about what we were doing last section with graphing functions, and I told you in 7th grade they're all going to be linear. We know they're linear because all of them have regular old operations, such as, I'm making this one up, y equals 3x minus 5. There's nothing super fancy going on there. It's just multiply by 3, then subtract 5, and then you'll have your y value. So because there's nothing fancy, it's going to have a constant change when you go to graph that. This idea of constant change, this unit rate, these relationships, it doesn't change. So just know, every time this input goes up by 1, this is consistent. One last final thought I want to leave you with is I want to remind you that when calculating these, it's going to always be your change in output, or your vertical. If you're looking at a graph, it's going to be vertical change. So I'm going to put vertical change over horizontal change. That's if you're looking at a graph, okay? Vertical change over horizontal change. I'm abbreviating. So that's if you're looking at a graph. Okay, sorry for how sloppy that is. Now, if you're looking at just a table, okay, it's going to be your output change on top and your input change on bottom. So if you're looking at a table, or even ordered pairs like this, if we were looking at ordered pairs, same thing, okay, it's going to be your, we said output change on top, so change in output. So output change is on top, and on the bottom will be your input change, or change in your input. That's the values you use, and you make yourself a little fraction, then you can interpret that fraction. But that helps you remember the order of it, because if you know the order of it, you now can say, remember, we got dollars over months, so you can say dollars per month. Because if months had been on top, we would have said months per dollar. So the order does matter, because it means something different if you change the order of it. So if you just remember vertical change over horizontal change, or output change over input change, or change in Y over change in X, that type of stuff, thinking of it that way, that'll help you stay organized in the order you do your constant rates of change. So put this into practice and practice these problems, and you'll be just fine. Good luck, guys.